I'm going to talk to you about how this new guide from the ISTRUCT, how to calculate embodied carbon. So myself, Orlando Gibbons at Arup have written the guide, and just to reiterate my thanks to those people who've helped us by reviewing it over the past couple of months. In the next 12 minutes, perhaps, I'll try and be as quick as I can. I'll give you a bit of the context, why we wrote the guide, what the minimum scope of a calculation is, and then talk about what's coming next, a teaser for what's coming next. Now, you all know about the Climate Emergency Declaration, which sets out a whole bunch of things that we are signing up to, seeking to achieve in the coming months and years. And I wanted just to highlight 4 of those. So the declaration says that we will seek to share knowledge, research on an open source basis. And to that end, this guide is freely available. Anybody in the world can download it, don't have to be an ISTRUCT member. The declaration also says we should include whole life carbon modelling as part of our basic scope of work. And so the guide therefore supports our practitioners in achieving that by giving you a method to do the calculation. By doing the calculations, we hope that you will see where carbon hotspots exist, and that will help to accelerate a shift towards low carbon materials in all the work that we do. And similarly, by seeing where carbon hotspots are in your designs, you can reduce or minimize wasteful use of resources. Why did we need to write this guide? Well, one of the key reasons is consistency. So there's lots of different ways of measuring carbon, embodied carbon. There's lots of different ways of reporting it, different components of your design to consider. And that can create problems for clients when they're trying to compare across designs. It can create problems for design teams. And so the guide is really about consistency, providing a common calculation method for us all to follow. Now, from that common calculation method, and actually it doesn't matter if it's, in inverted commas, the right calculation method, it's just we all do it in the same way, we therefore have an ability to have meaningful design comparisons. We're comparing apples with apples and not bananas and gorillas. That common calculation method hopefully improves our understanding of carbon, supports material demand reduction, and the more people that get involved in this, the better chance we have to find new ways to reach net zero. So in the guide, we set out 7 principles, and I'll just run through those quickly, that we hope people who use the guide will follow. So the first principle, of course, is we must achieve net zero by 2050. I don't believe there are any negative emissions technologies, so this is an absolute target. We must reach absolute zero by 2050. This guide needs to be applied to every single project you do, not just the flagship projects, but everything from the garden shed through to the office block. And it's important to remember that carbon and counting carbon sits as part of those UN SDGs that Mike and Will have already explained. So it's not solely about, sustainability is not solely about carbon. There are lots of other aspects to consider. Once you've done your calculation, it's really important to use that calculation to weigh up design decisions. So the classic example is future flexibility versus upfront carbon. So make your design decisions based on a calculation of the carbon impact. And once you've done your calculation, it's equally important to communicate that to your design team. Tell people what you found out. There's no point working out the embodied carbon of a concrete beam if you don't tell anybody about it. And it's no point doing it if you don't use that calculation to drive reductions in embodied carbon. That's why we want to have this guide. And finally, an internal discussion around designs is of course important, but we must also tell the world about our designs. So reporting on an open source basis, the embodied carbon of designs is equally important as doing the calculation. Now, Will has stolen my thunder with this slide. So the point here is that the potential for your professional impact is huge. So these are things you can do in your private life, and of course, go away and do them. That's absolutely correct. But if your professional practice doesn't reflect the same ideology, then we have a problem. So the scope for structural embodied carbon reductions is huge in terms of carbon savings per year. So really important that everybody engages with this. Now in the guide, we've set out a flow chart, that you see on the right-hand side of the slide here. And that flowchart we feel can be applied to every project that you do. And I just want to tease out a few important points on that flowchart. So in the bottom right-hand side, you see this box which says feed into next project. And for me, that's really important. Don't view your calculation of embodied carbon as a standalone object. View it as something where you can learn a lesson and feed that into your next project. Perhaps you tell other members of your design team as well. Now, if we go back to the top middle of that diagram where it says start, you'll see the first thing under the start box is consider the brief. So we don't leap into a calculation. We think about, is this the right thing to be doing? So the option studies, the default options we put here will be do nothing. That's a really great way to get to net zero or zero carbon, is to do nothing. Achieve your client brief by not building anything new. And so that's the sort of the message of not just about calculation, but also reductions. For each of your options, you go through a process of calculation, of analysis, communicating and discussing with your design team, pursuing the lowest carbon options, and then reducing and refining. So here the message is that calculating embodied carbon needs to be an iterative process. You don't just do it once in the design, you do it all the way through. And hopefully when I show you the calculation itself, you'll see how that is something that can be embedded in your design processes. So really important that it's not just done once, it's done early on, and it's done frequently. Now, the guide doesn't cover every single stage in that flowchart diagram. The bits that are now highlighted in green are our focus, of course, the calculation and the communication and the reporting. And in the guide, if you've looked at it, you'll see that there's a few kind of key principles which we highlight in green. I've just put one on the screen here. That to not be deterred from doing your calculation because of any uncertainty in material quantities. Just to reiterate the point, the earlier you do your embodied carbon calculation, the better. That gives you scope and time to make changes. If there's no scope to do a change based on the calculation, then it's a real problem for us. The guide, if you've downloaded it, you'll see the contents page looks like this, and we've used the same headings as the flowchart diagram to try and make that easy to follow, easy to navigate, and of course, please give us feedback if you have used it and looked at it. Now, this guide doesn't sit in isolation. There is other guidance on embodied carbon, particularly from RICS around whole life carbon assessment, but also some design codes, and very recently from LETI, the London Energy Transformation Initiative, design guidance around low carbon design, really worth reading. So the point here is that the ISRT guide is intended to be non-contradictory and complementary to all this other guidance out there. So please read other things as well as the ISRT guide. The guide itself covers the entire scope of whole life design. So we talk about all the various modules and stages of the whole life of a building. In our document, we say that the minimum scope of the calculation for somebody following this guide is modules A1 through A5. So those are what we would call the upfront carbon of a design. And there's an important reason why we've made that the minimum scope. These are the emissions that will be released certainly before 2050. We have great certainty over them. And when we're talking about pure structural engineering, this is where the majority of structural embodied carbon comes from. So modules A1 to A5 are really important. Now, if you're doing a facade design, you would include module B4 as well. That's the replacement in use. Now, having said that, as a minimum scope, A1 through A5, there is also very clearly written in the guide, the best practice remains to consider the whole life cycle of a structure. But we didn't want that to be a barrier to doing the calculation. So the minimum scope is A1 to A5. Best practice remains to do A to C plus module D. So since the minimum scope is modules A1 to 5, I'm just going to show you how the calculation works. And so hopefully this will build up gradually on the screen. And I'll give you a sense of some of the notation that we use. So embodied carbon for life cycle modules A1 to A5 is calculated by taking the sum of all the materials in your design, so 1 through to 949, and you take for each of those materials the quantity of material, probably measured in kilograms, which you take from your calculations, and you multiply that quantity by 3 embodied carbon factors. The first of which is the embodied carbon factor for modules A1 to 3, and that's usually measured in kilograms CO2 per kilogram, and you can obtain that kind of data from a database or an EPD. You also multiply your quantity by the embodied carbon factor for module A4, which is transport for that material, and you work out your embodied carbon for transport based on how far your material has been transported and by what mode it's been transported. So that's really talking about supply chains. You also multiply your quantity by A5W, which is the on-site construction waste, and that's calculated using some formulae from the UK net waste tool. Now my screen's gone very pixelated, but hopefully you can still see that. That's all multiplied by the quantity of material, and on the end we add a final factor, which is the embodied carbon for module A5A, which is the on-site construction emissions. Now this is not multiplied by the quantity of material because it's calculated based on the project value, and that's following the RICS approach to doing this. So as you can see, that's a very simple equation. It's adding and multiplying various factors. It's really well suited to an Excel spreadsheet or similar, and can be quite easily embedded into your design process. Now, once you've done the calculation, as we said, it's really important to tell people about it. And so in the guide, we provide some examples of how you might present these results. So modules A1 to 5, you might present including sequestration underneath. You always tell people how you've normalized your results. So in this case, by GIA. You tell people what the scope is, so substructure, superstructure in this case. If you are doing module D, it's always reported separately for reasons which we can discuss in the Q&A. Once you've done your calculation, as I said, it's important to report this not just internally but externally, so please submit your data to an open source database. And the intention here is that every single building in the world has the potential for an embodied carbon assessment. The more data we have, the better chance we have of establishing benchmarks, seeing where good practice is, and learning from each other across the industry. So we propose in our guide that people should report their results to the RICS database, and myself and Orlando are currently working with RICS to improve and update this database as well. And so my final slide then is to say what's next. On the 7th of October, myself and Orlando will be delivering an evening seminar, and please sign up. This will include some real-life project examples from Orlando's work at Arup. And also please download the guide and read it, and there's a short link on the screen. Thanks very much.
Thank you, John. And good to see a nice big equation on the screen to kick us off with some proper structural engineering. I think the key takeaway message, if I'm right, is that we should be trying to calculate the embodied carbon in our design, regardless of what stage we're at, no matter how uncertain the data is, and the earlier the better. Is that that's sort of fair to say?
That's a very good summary, yes.
Thanks, Will, and thanks, John, for that intro. That's great. So thanks for joining us, everyone. It's great to have you all here and engaging with the issue of carbon in buildings. So for those, like Will said, for those of you who don't know me, I'm a practicing chartered engineer. I work at Build Collective, which is a small bespoke consultancy based in Bristol. I specialise in timber frame structures, and I just wanted to show you some pictures of sort of projects that I'm working on. I've done around about just over 15 passive houses and other certified ultra low energy buildings, new builds and retrofits. Hopefully you can see some of them. As most of them are one-off new build domestic developments, but we're currently looking at visitor centre, tennis clubhouse, social housing. So whilst what I'm saying today, it will be mostly dwelling focused, it can be applied to all sorts of different buildings. Okay. So this is what we're going to look at today. So we're going to look at a comparative balance of operational and embodied carbon and the contribution to the whole carbon impact of a building. We're going to look at some components of operational carbon, breaking that down into some different sections so we can see where the energy is used. So where energy is used in the lifespan of a building. And finally, we're going to look at what we as structural engineers can do to help reduce operational carbon usage, and using the example of thermal bridges. So first up, we're going to look at the balance of operational and embodied carbon. So here's a picture of what the operational and embodied carbon contributions look like to the whole building picture over a 60-year lifespan building built to current building regulations. And you've got a few different types of building typologies there. These charts are from the LETI Climate Emergency Design Guide, which John mentioned as well. It's a great document, and I recommend you all read it. I'm going to use a lot of data from that document today, and I'm going to focus on the middle pie chart there of the medium-scale residential data, because that gives the largest contribution of embodied carbon once we've reduced the operational carbon, and I've seen it used in an iStruct journal before. So you'll notice the proportions on this chart look quite different to some of the other charts you might see around. This is because the LETI guidance uses actual usage data rather than design energy usage data or modelled energy usage data. and our operational energy models in current building regulations can give actual energy usage anywhere between 40 and 500% greater than design usage, depending on who you ask. If you Google search for the performance gap, you'll see charts like this one, which show that it's showing the annual energy usage for various different buildings in those EPC ratings. And you can see that the EPC rating doesn't correlate to how much energy the building is going to use. There's a whole discussion around that, which I won't get into, but it's just something to be aware of when you're looking at the operational carbon data of buildings. So going back to the LETI data, this is the same LETI data, just presented differently. I find these charts easier to get a handle on. This is the medium scale residential development data. So the operational carbon is roughly 66% of the lifetime carbon picture for a 60-year lifespan building. And then if we look at the savings we need to use to meet the LETI guidance, again, looking at what an ultra-low energy building would look like with carbon reductions. And this is the sort of scale of the savings that we need to make. So we're making roughly 87% of the savings in the operational carbon section, and then we're making roughly 13% in the A1 to 3 embodied carbon section, of which that 13%, 7% of that is the structural. So yeah, just over half, like Will said at the beginning, is the structural materials. So now we've got a picture of where we are with the sort of balancing operational energy and carbon. I'm going to talk more about operational carbon and what we can do to as engineers to reduce that. So here we are. Let's move on. So this is what you can see where the energy demands that make up the operational carbon chunk of the whole life carbon how it sort of splits. So most of the sections you can see on the side are self-explanatory, but a couple might not be immediately clear. Auxiliary energy is the vague title for any pumps and fans which are needed to keep other things running, like air conditioning fans and boiler pumps, all that kind of thing. Unregulated energy is energy which is unregulated by our current building regulations. So it's basically anything that plugs in. So electronic devices, lifts, although I'm not sure how they plug in, but yeah, refrigeration systems, cooking equipment, anything like that, which our current building regulations don't currently deal with. And we're going to focus on that 60 to 65% heating demand portion now, and break that down some further, so we can have a look at how structural engineers can impact this carbon demand. So more pie charts. This is the that heating section broken down into the distinct parts. So this is what makes up the heat loss of a building, and therefore what our heating demand of the building is. So we can see that sort of almost 50% of that is the fabric losses, i.e. what's lost through the planar building insulated elements of the building, such as the roof, the ground floor, the walls, the windows and doors. So that's described as the U value for that element. And then we've got the thermal bridges, which is about 25% of that section, and I'll describe that in more detail later. And then we've got the ventilation and infiltration losses. So ventilation losses are the heat loss through providing sufficient ventilation for the occupants of the building, through things like trickle vents and purge extract fans in kitchens and bathrooms. That tends to be how we deal with it at the moment. Infiltration is the unintentional or accidental introduction of outside air into a building, also referred to as air leakage. So both of those elements are related to the air tightness of a building. So note the numbers as well as the percentages on this graph. These are in kilograms of CO2 equivalent per metre squared. These are based on the current building regulations using LETI data. I tried to make the next graph for an ultra-low energy building proportional to size, but it just wouldn't have been legible. So here we are, giving some idea of the scale. So these are the proportions for those categories for an ultra-low energy building, as defined by LETI. So you can see in the numbers we have a significant reduction in energy demand, operational carbon demand. So we're talking about a change from just over a tonne of CO2 per meter squared to 46 kilograms for the heating demand. So you can get an idea of what the scale of the reductions that we require. So reducing fabric losses is basically reducing the U values. That's quite straightforward. Add more insulation. And engaging with air tightness means reducing ventilation and infiltration losses, and that's more that I've got time for today. So what we're going to do is pull out that thermal bridging section and look at how we as structural engineers can engage with that. So first of all, what is a thermal bridge? A thermal bridge is a line or a point of the building fabric which has a worse thermal performance than the building fabric around it. These usually occur at junctions or connections between different building fabric elements and penetrations through thermal elements. So for example, water floor details, water foundation details, roof to wall details. The thermal bridge is measured in watts per meter Kelvin for linear thermal bridge, or watts per Kelvin for point thermal bridges, to compare that to a U value, which is in watts per meter squared Kelvin. Uninsulated buildings have no thermal bridges, as you can sort of see from that picture there. The difference between the thermal bridge is limited compared to the U value of the wall around it. As we increase the U values, the thermal bridges for the same junction have a larger impact on the heat loss for that wall element. So shown in the example of a windowsill here, this first image is of the original condition of an uninsulated wall. You can see that the U value is poor, but the psi value, the thermal bridge, isn't significant. And then if we look at that same junction, but with external wall insulation added, that's the EWI, you can see that the first image, there were no changes made to the original windowsill detail. So you can see on the right, the thermal bridge has significantly increased from the original condition, whilst the U value of the wall has lowered. And then the lower image, the window has been moved out into the insulation zone. The sill has been cut back. And I assume the window is supported on some kind of dense insulation, foam glass or compact foam. And so you've got a more continuous insulation line, your window being part of the insulation line of the fabric. And so you can see the significant reduction in the thermal bridge psi value for that junction. You can see on the screen there the passive house thermal bridge free definition of a psi value. But this is a graph which shows essentially the same thing. This is the thermal bridges in here are defined by the Y value, which is how our building regulations deal with them, which is the total number of thermal bridges for the buildings divided by the floor area. And you can see here, if we increase the U value of the thermal elements to something like 0.1, which is what would be required for an ultra low energy building as defined by Letty, you can see that the thermal bridges could account for 50 to 60% of the overall heat loss if we design to our current building regulations. That's a significant potential carbon saving, which is open to structural engineers. And I'll give you an example now of how we can engage with that topic. So here are some examples of common thermal bridges supporting windows in the insulation zone, as you've just seen. Steelwork generally, it's difficult to deal with, but particularly columns to foundations and any kind of overhangs that you might have, balconies, roof overhangs, that kind of thing, cantilevers of any kind. Steel strapping, holding down straps, masonry restraint straps, they can all go through the insulation zone. Insulated cavity wall lintels like these with the continuous steel plates running from internal to external. And temporary works elements that come in and add significant structural elements that weren't necessarily accounted for in the original design conditions. That's a crane base on a pressurized element on that picture there. So let's look at how we deal with those. So here's what I do when I get a new project. This is a section from one of my current projects where I've marked out the insulation in pink and the steelwork in red and the concrete in green. So first steps, mark out where the insulation is going, and then highlight any areas where the structure is crossing that line. Ideally, the architect would do this for you, mark out where the insulation's going, but there's no harm in having two sets of eyes looking for thermal bridges, and being prepared for potential problem areas ahead of somebody else telling you about them. So here you go, we can see that the steelwork is causing problems to the insulation zone. So do this initial review in plans and sections, because some thermal bridges will only occur in one plane. And then repeat that process every time you come to another level of detail. So when you've moved on from looking at the overall structural solution, then once you come to look at the details, looking at cladding fixings, looking at restraint straps, those kind of things, go again the same process. Where am I fixing through that insulation line? And that's it. It's quite a simple process to identify thermal bridges. Hopefully it'll give you an idea of where we need to go. And then let's look at one specific thermal bridge just to finish. So you can see the scale of the impact of one thermal bridge. So this is a standard detail from a timber frame mass house built house. The wall to foundation junction with the ground floor there as well. The thermal bridging allowances to the minimum standards, i.e. building regulations. And I've highlighted the insulation in pink there, so you can see quite quickly where the area of low insulation is at the side of the floor slab. So there you go. The side values of the junction is there, and then so that for a two bed 4-person dwelling for social housing equates to a lifetime carbon usage of roughly 20 kilograms per metre squared, and that's assuming that the building is heated with an air source heat pump. So let's compare that to a thermal bridge-free detail for a passive house or an ultra-low energy building as defined by Letty. So here's a common detail from timber frame passive houses. The main change here you can see is the foundation solution has been swapped from a standard strip foundation to an insulated raft foundation. So that gives a really good thermal bridge-free junction and an easy airtight junction as well. You can do a visual check to see the potential thermal bridge here, and you can see that there's the same thickness of insulation down underneath the slab as there is up the side of the slab. So you can see, we're just looking at it quickly, that we've already reduced the thermal bridging. So the wall in this case is an I-joist wall, but it could be a solid stud wall with external insulation. It could be a Larsen truss wall. It could be a twin wall truss. It could be CLT. Doesn't matter. Any of those would work with this. And we can see the dramatic reduction in carbon per metre squared. And that gives a lifetime carbon saving of roughly 1.5 tonnes per dwelling. So think of how much carbon we could save for like a housing development if we looked at this kind of detail differently and impacted the operational carbon usage this way. So to sum up, I want to propose this checklist to help structural engineers engage with operational carbon as well as embodied carbon. So first of all, set performance standards and targets. Do you know what they are for your project? Do you know what U values, what thermal bridging values, what airtight level you're trying to achieve? If you don't set some standards, even if it's just in-house, you know between your design team what level of thermal bridging or airtightness you're aiming to achieve with your details. Material choice, which is very linked with embodied carbon, but also impacts operational carbon. Is it appropriate to the layout? Is it being used efficiently? There'll be more on that in later presentations. So get to know the insulation and airtightness strategy. We've had a look at the insulation strategy in that section, but also true for airtightness. And get stuck into the details. This is where you're going to impact most of the operational carbon of the building. Looking at the impact of each strap. I just want to finally say that if we start to engage with operational carbon, we can transform our impact over the lifetime of the building from something like this, adding in thermal bridging, to adding in engaging with the U values and the fabric, and then finally to engaging with airtightness as well. And we can change our impact from just a small section to a massive section for a 60-year lifespan building. Thank you.
Thank you, Beth. And yeah, really good. I don't imagine you'll be the only speaker today to reiterate how important it is that we think beyond just being a structural engineer. And I like the fact that you made the point, of course, that so much of this applies to house building, which is such a big part of the structural engineering industry. I think last year something like 170,000 homes were built in the UK alone. And so if you can save a ton of carbon on each of those, it's clearly worth doing. So thank you for that. So we've got about 7 minutes or so to do a bit of Q&A. So we've got a few questions coming through. I think the first one to pass on would be to John. So John, I've been asked, embodied carbon, is there any concern that by adopting an A1 to A5 as minimum scope, that this is where most people will stop their calculations? And maybe you could comment on consideration around other stages such as B1 or D to ensure that we don't pass the problems on to future generations.
Sure, thanks, Will. Yeah, this is something we thought about a lot, and I guess it's important to say up front that the best practice is, of course, to consider modules A through D, but just to be aware that there's decreasing certainty over what's happening in the later modules, so particularly C and D. And so, because we don't really know what's going to happen in the future, we absolutely don't know. It's basically saying that the structural embodied carbon, the carbon that the structure engineer has his or her hands on, is mostly around that upfront carbon, modules A1 through 5. And so that makes it a good place to put the minimum scope, of course, adding B4 if you're doing facades. So we're not saying you shouldn't do A through D, we're absolutely saying you should do it, but just simply that the minimum scope, which enables you to cover the bulk of the emissions, is A1 through 5. Now, in terms of passing this problem on to future generations, I completely understand the point that was made there. But again, we don't know what's going to happen in the future. Perhaps there'll be some brilliant new material we can use to retrofit our buildings in the future, and our module D assumptions we make now will be completely incorrect. So there's a balance between the certainty around the emissions and the uncertainty around what will happen in the future.
Thank you. And that leads quite nicely on to the next question I've got, which is to do with the sort of split between operational and embodied carbon. I guess maybe this is one for Beth firstly. So Fernando Perez has written, typically the MEP consultant wins the discussion to build newer, higher embodied carbon structures, arguing that in the longer term, the operational carbon over the 50 or 60-year life of the building will balance that out and overall would be lower. But however, we saw on Mike's introduction, the challenge is, of course, now not in 50 or 60 years. So what's your view on the importance of embodied construction carbon now versus the longer term effects of operational carbon? I don't know, Beth, do you want to respond to that first, maybe?
Yeah, sure, I can do. Yeah, so on those quick graphs I showed you at the end, yes, for a 60-year lifespan building, the operational carbon is a significant impact of the overall carbon lifespan picture of the building. But I don't think it's an either or. You can build great low embodied carbon, low operational carbon buildings that will also lower embodied carbon. It's not one or the other. Hopefully we can look at these as extra things that we can look to reduce the carbon in, rather than a either or debate.
Thanks, Beth. John, do you have anything to add to that?
Yeah, I think the important thing to be aware of is that the bulk of our carbon savings have come through decarbonising the grid, right? So that's where our operational energy is being used. So the more we decarbonise the grid, the better. So in theory, if your energy supply is zero carbon, then actually the energy use doesn't matter so much anymore, because the carbon is neutral. So there will be ever increasing energy requirements or carbon requirements on the operational side, and so it's the embodied part of that picture which I feel is now the most important bit. So decarbonising the grid is going to really help us with operational energy, basically.
There's a grid presentation on that, by the way, which is done by the Passive House Trust, John Palmer from the Passive House Trust. If you search on their website for Passive House and Net Zero, or Google Passive House Net Zero, there's a great presentation about the impact of decarbonising the grid and how that affects our building energy usage.
Fantastic, thanks. I guess on the question of sort of other things to go and watch, we've had a question of are there any good guidance documents out there on the baseline of embodied carbon usage? I guess that's one for John. Where should people go now if they want to try and understand what low carbon design maybe looks like and what they should be aiming for?
Yeah, so that's a really great question, and that kind of takes us back to that database. So for everybody listening, what we really need is data on what's really going on right now. So the RICS database has somewhere around a few hundred data points in it, which is minuscule in comparison to the number of buildings we do. So the quick answer is we don't really know because we haven't collected the information on any big scale. So the call to arms, I guess, is please tell us what you're doing. Once we have that information, we can then obviously understand a bit better what's good and what's not so good. In terms of guidance you can look at right now, the two key places that both Beth and I think have highlighted are obviously the RICS guidance, so the surveyors, and also the LETI recent publications around what they call climate emergency design, which covers a few examples of embodied versus operational carbon. And there was very recently, actually just a few weeks ago, a report from UKGBC where they looked at a design example and tried to see how they would get to net zero. And it was a pretty honest report about some of the difficulties that they had with a real project. So there is stuff out there. So UKGBC, LETI and RICS would be three places to look.
Thanks, John. And Beth, do you have any last thoughts on favourite guides to send people towards from a minimising operational point of view to go with that?
I guess any information by the Passive House Trust is great because that's what they are looking at. The whole Passive House standard is reducing operational carbon. Looking at the comparison of operational energy and operational carbon is interesting, like John's presentation with the Passive House Trust. And LETI, the LETI guidance is just brilliant. So that too.
Fantastic. Okay, thank you both. So we're going to move on. I guess to summarise the last 45 minutes or so, this is about doing the numbers. So any questions you ever have on operational versus embodied, how to minimise one or the other, or any conflicting thoughts you might have over this idea has more thermal mass, that's more embodied but lower operational, how do I do it? You can do the numbers, and we should. We're engineers, we should be doing the numbers as we do with all other aspects of our design.